2.2c. Now this one kind of is the culmination of all the other lessons combined. So this is really where we're going with this whole module, is trying to take a linear context, which just means basically a story. Take a story and then put it into a linear context, which means table, graph, and eventually equation. So just remember those three things: table, graph, and equation. That's what we're going for on every problem. So Jack's filling his empty swimming pool, so I'm going to start right here. If 0 minutes, he has 0 gallons of water. That should tell you a bunch of stuff. First of all, 0, 0 means that it's going through the origin. That means that this is going to be a proportional relationship. Let's see what else it says. And he's being filled at a constant rate, 4 gallons per minute. So that right here should tell you all the information you need to know to fill out this table. So every time a minute passes, 4 gallons. 4 more, 4 more, 4 more, and so on. So now, let's do what I showed you on the last lesson. Right here, this change from 1 minute to the next and this amount of gallons to the next, this goes up 4 gallons every time this goes up a minute. This goes up 4 gallons every time this goes up a minute. I'm going to do something else though. I'm going to skip. If I went from 4 to 6, that would be 2 minutes. And if I went from 16 to 24, that would be 8 gallons. Well, if I simplify this rate of change of 4 over 1, it's just 4. Isn't that the same as 8 over 2? So you can pick really any two pairs and you're still going to get the same constant rate if you simplify it. So graphing, 0, 0. 1 minute, 4 gallons. 2 minutes, 8 gallons. That's just these ordered pairs. And another way I can do it is just know that every time I go 1 more minute, I go 4 more gallons. And just be careful. Notice that this is in increments of 8 to 10, 10 to 12. So 1 more minute, 4 more gallons, etc., etc. So now we've got 624, which is right here. And actually you should understand that the pool is filling constantly, so you can connect this line, these points with a line, knowing that actually between 0 and 1 minute there is still water running. Okay, so I'm going to put a couple of things in here that you already know. The equation now, we're going to use x and y. Is going to be y equals. So what is the rate of change of gallons per minute? And this table shows it. The story up here shows it. It's 4 gallons every time a minute passes. And now, does this pool have a head start or did it fill empty? And as you can see, 0, 0 means that there's nothing being added in this equation. It's just y equals 4x. And you could test that, is just pick any x and plug it in and make sure it works. So 4 times 5, for example, would give us 20. Is this context linear? Absolutely. Use evidence from the story, the graph, and table to support your answer. So in the story, what does it say in context? Well, those words right there, in context, it says constant rate. The graph just shows that it's a line. You can actually see the line. And then the table, this constant change here of the rate of change is the same, is constant. It's the gallons per minute is always 4 over 1 or just 4 when you simplify it. Alright, how would you change the context of this problem so it could be modeled by the equation g equals 4m plus 2. So I guess they're calling this g and then they're calling this m. So I'm going to put the y and the x in parentheses there. So just don't get your variables mixed up. So gallons equals 4 times the minutes plus 2. So tell me what would be happening first of all. If we have the same number multiplying here and here, is it filling at the same rate? And your answer, of course, should say, yes, it's filling at the same rate. So what's different about this equation from this equation? And hopefully you're noticing this. And what does that little 2 right there mean? That little 2 means you started with what? 2 gallons. It wasn't an empty pool. Started with 2 gallons. So this equation right here would not start here at 0, 0, it started 0, 2, so it wouldn't go through the origin. Okay, next page, a nice story about an airplane. I like airplanes. Airplane is at an elevation of 3,000 feet. And then it's showing its elevation for every 2 miles it travels. So be careful here. This is going 2 miles at a time, not 1. So this is 0 and this is 3,000. So clearly this is not the origin. So what's happening here is it's going 2 positive miles as it's traveling, but what's happening to the elevation here from 3,000 to 2,000 is going down 1,000 feet. Well, guys, this rate of change, you cannot say it is this and this, because we're not talking about, if I said how fast is this plane changing elevation, obviously I put a negative here, and that's because 3,000 is going down to 2,000. Or I could say 2,000 to 1,000 is also negative 1,000 when this goes up too. But let's be careful about this because this is going 2 miles at a time. So we'll come back to this in just a moment. So let's complete the graph and see how many miles it takes the airplane to reach the ground. By the way, the ground is an elevation of 0, right? So 0 minutes in, 0 miles, he was way up here at 3,000. Then after 2 miles, he's now down here at 2,000. So if I kind of imagine the line right here, what about 1 minute, 1 mile? You see that it looks like to be about 2,500, and we'll come back to that in just a moment. 2 was 2,000, and then 4 is 1,000. And then let's continue here. So now, every time it goes down by 1,000 feet, it's got to travel an additional 2 miles. So 2 more miles, 2 more miles, down 1,000 feet. So now guess where I'm at. My elevation right here is on the ground. So how many miles would it take the airplane to reach the ground? And you can see he hits the ground after 6 miles. How is this shown on the graph? Well, it's, what's this axis called right here? It's going through or hitting the x-axis. All right. So now use the table and graph to find the rate of change. I have cautioned you that it's not negative 1,000. We're not losing 1,000 feet in 1 minute. We're losing 1,000 feet in 2 minutes. So what about in 1 minute? And clearly he's going from here to here, from 3,000 to 2,500 in 1 minute. So he's losing 500 feet per minute. Make sure you put that negative sign in there, because look, it's going down by 500 feet per minute. If you put a positive, the airplane would be going up. Well, I think we have all the information we need to write the equation. So just as a reminder, this is the rate of change, right? It says so here. So y equals, and I'm going to label this y and this x for you. Y equals my rate of change, negative 500, times x. And now, is it starting at the origin, or is it starting way up here at 3,000? And the answer is it's starting at the 3,000 and going down 500 per mile. So there's the 3,000 right here, and the negative 500 per mile is all these steps. Every time you go another mile, you go down another 500. Explain how the equation can be used to determine how many miles it will take the plane to reach the ground. So if I just wanted to use the equation, not the graph. If I wanted to reach the ground, remember the elevation is y, and reaching the ground is when y equals 0, right? If I want an elevation of 0, what could I do? Well, I could replace this right here, this y, with an elevation of 0. So instead of y equals, I put 0 equals negative 500x plus 3,000. By the way, we already know the answer. It's 6 miles. But here's the equation that we can plug it into to prove that. So I've got some stuff. I just got to solve this equation. So if I subtract 3,000 and divide by divide by negative 500, and divide by negative 500, this negative divided by a negative is going to give me what kind of a number? And of course you're going to say it's a positive, right? X equals 3,000 divided by 500 is 6, just like we said here. Okay, and then the last couple pages are going to give you a story and a table, and all we're actually going to do is complete the remaining 3 representations. That means either story, table, equation, story, table, equation. Okay, I'm going to press pause here for a moment. Okay, so you and your friends go to the state fair. It costs $6 to get in. Right away you should know what happens. $6 to get in is no matter how many rides you do, you pay $6. And then $2 each time you go on a ride. So every time you go on a ride, it's an additional $2. So careful here. So $2 per ride, from 0 to 2 rides is not $2, it's going to be 4 additional dollars. So that's going to be 10, because it's not 1 ride, it's 2 rides. And then 2 more rides would mean 2 times 2 is 4 more dollars. And then 2 more rides is 2 more dollars, 4 more dollars. This is my unit rate, is 2. Okay? So now, they're saying complete the equation and the graph. So using the data points, just plot these points, 0, 6, 2, 10, etc. So 0, 6, 0, 6, 2, 10, 4, 14, 4, 14, and 6, 18, right? 6, 18. There's our graph. There's the $6 to get in, and there's the additional. Look, every time we go on one more ride, so this is 2, 4, 6, 8. If we go on 2 more rides, we would have spent how much more money, right? Oh, let's make sure that we label some other stuff here. This is our y-axis, this is our x. So our y is the cost, this is the cost, and this is the rides. So one ride, one additional ride, if I kind of like imagine my line right here, one additional ride would go from $6 to $8 would be $2 right here. This little stair step. There's my unit rate. And let's write an equation. Well, I'll need that piece of information, and I need the unit rate. So what was my head start, and what was my unit rate? So my unit rate is $2 per ride plus my head start of $6. And then it says how many rides can you go on if you have $25. Remember, the cost is the y, so I'm just going to replace y with 25 equals 2x plus 6. So you subtract 6, and this is going to come out a little weird to you, you might think, because 2 doesn't divide into 19 evenly. X equals, what is that, 9.5? So you can't go on 9.5 rides, so you can really only go on 9 rides. I think we actually answered all these questions already. What is the rate of change in the problem? It's $2 per ride. What does the rate of change represent in the context? How much per ride? What is the y-intercept of the graph? Underline that word. Circle this question. The y-intercept is the point where your graph starts. So, sorry about the video. Underline this word. Y-intercept is where your graph hits the y-axis. Where do you see the y-intercept in the table and in the equation? So on the graph, it's where it hits the y-axis. Where do you see it in the table? Where do we see it in the table? Right there. That's the y-intercept. Where do you see it on the equation? And in the equation, that's the y-intercept. Make sure you label everything I'm doing. Okay. What does the y-intercept represent in context? That is the price to get in. And I've been using the words Head Start all the time. All right, last two questions here. So how would you change the context of the relationship between the total cost and the total number of rides is just 2x? So what happens to the story if I don't have anything being added here is that there is no entrance fee. In other words, no fee to get in. And then letter D, how would you change the context of the relationship with the total cost and number of rides as modeled by the equation y equals 6? So guys, this doesn't mean that y equals 6 times x. This just says y equals 6. So what that means is you pay $6 and there is no fee per ride. Just $6 to get in and ride all you want. Okay. Bowling, you're going to write a little story here. We're going to do all these pieces right here, and then you're home. So I'm sorry this is taking a little bit. It's 16 minutes so far. So quickly, looking at this table, the first thing I notice is that every time I play 2 games, it costs me an additional how much money? So that's $4 for 2 games, right? 4 more bucks, 2 more games. So it costs $4 to bowl 2 games, right? $4 for 2 games. But there's a little more to it than that. Let's follow the pattern here and go backwards. 2, 4, 6, 8, it's going up by 2. So if I went down by 2, what would this have to do? From 11 to what? Wouldn't there have to be a 7 if it followed the pattern? So it costs $4 to bowl 2 games, and, well, what's this $7 for bowling? Maybe it's $7 to rent shoes. So you got to rent the shoes. They won't let you bowl without it. Trust me, I know. I've been yelled at for it before. So $7 to rent the shoes, and then you pay $4 to bowl 2 games. Okay, let's go ahead and graph this relation. 0, 7 would be right here. There's the y-intercept, by the way. Oops, sorry. $2, 2 games costs me $11. So that's the cost on this axis. 4 games costs me 15, and now I'm pretty much out of room, so I'm going to just try to kind of guess where 6 games for 19 would be. It would be somewhere in that. I'm just kind of following the pattern, right? But now, what's the cost per game? What is the rate of change in this problem? So if it's $4 for 2 games, isn't that $2 per game? And what is the rate of change representing represented context? It's just what we said, $2 per game. What does the y-intercept of your graph? The y-intercept of our graph is 7. The y-intercept of our graph is right here at 7. Y-intercept. Where do you see the y-intercept of the table and in the equation? Well, on the table, I see the y-intercept right there. In the equation that I haven't written yet, we are going to have to add that $7 in. So let's write our equation now that we have our rate of change. Y equals 2x plus 7. So our y-intercept is this 7 here, this 7 here, this y-axis point right there. Okay? And what does it represent in context? That's the shoe rental. All right. Last couple questions. How would your context change if the rate of change was 3? Well, what would happen is it would be $3 per game. How would the graph change? Well, the graph wouldn't be going up $2 every time. It would be going up faster. It would be a steeper graph. It would be steeper. So if the rate of change is 3, how many games can you play for $20? So now if I said, using the same context, the $7 shoe rental, if I said y equals 3x plus 7 instead of 2x plus 7, because they're telling us to, and they want to see how much money, how many games 20 bucks will play, you just replace the y with 20 and solve that equation. So subtract 7, you got $13 equals 3x. Divide by 3, so 13 divided by 3 is what? 4 1/3. So you have enough for 4 1/3, but you can't really play a third of a game, so you'd only be able to play 4 games. And last but not least, describe in words what a linear relationship is. Think about all the equations you have written. What do they have in common? What are the different parts of the equation represent? Well, we're going to talk about that after you do your homework. So this question I'm going to leave blank for you on purpose, because that's something for you to think about, not for me to answer. Sorry about the 21-minute video.